Hello there and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore one of the most extraordinary and most quietly unsettling discoveries in the history of physics. A discovery that begins with the darkest objects in the universe, regions of spacetime so extreme that nothing, not even light, can escape, and ends in a place where the nature of information itself and the deepest relationship between quantum mechanics and gravity remains one of the great unsolved mysteries of our age. This is the story of black holes. And more specifically, it is the story of what happens when you combine the physics of black holes with quantum mechanics, when you ask not just what a black hole is, but what it does over time, what it emits, how it ages, and what ultimately becomes of everything that falls inside. It is the story of Stephen Hawking, who in 1974 made one of the most astonishing theoretical discoveries of the 20th century, that black holes are not perfectly black, that they glow with a faint thermal radiation, that they slowly lose mass and energy over astronomical timescales, and that they will eventually, after an incomprehensibly long time, evaporate completely and disappear. It is the story of Jacob Bekenstein, a young Israeli physicist who first proposed that black holes have entropy, that they carry within them a vast quantity of hidden information about everything that has ever fallen inside. It is the story of the information paradox, the deep tension between general relativity's picture of black holes as perfect information destroyers and quantum mechanics' insistence that information can never be truly lost. And it is the story of the holographic principle, the remarkable suggestion arising from all of this that everything happening in a volume of space is somehow encoded on its boundary, that the universe we experience in 3 dimensions is, in a precise and technical sense, a kind of hologram projected from a 2-dimensional surface. These are among the deepest ideas in all of physics, and they are ideas that can be approached with patience and care using the tools of high school mathematics and the technique of dimensional analysis, the physicist's art of constructing equations from the fundamental constants of nature without doing the full calculation. We will use these tools to derive the area of the black hole event horizon, the entropy of a black hole, the temperature of Hawking radiation, the power output of an evaporating black hole, and the evaporation time, all from first principles, all from the basic dimensions of the physical quantities involved. So settle in. Let your body grow heavy and still. Let your breathing find its own slow rhythm. And allow the story of black holes and Hawking radiation, of the darkest objects in the universe quietly glowing with quantum light, of information encoded on horizons, of space-time and quantum mechanics meeting at the edge of the knowable, to carry you gently towards sleep. To understand black holes, we need to begin with gravity. Not gravity as Newton understood it, as a force acting across empty space between masses, but gravity as Einstein understood it, as the curvature of spacetime itself in response to the presence of mass and energy. Einstein's general theory of relativity, published in 1915, was a revolution in our understanding of space, time, and gravitation. Newton had described gravity as a force, instantaneously transmitted across any distance, pulling masses toward each other in proportion to the product of their masses and inversely proportional to the square of the distance between them. This picture was extraordinarily successful. It explained the orbits of the planets, the tides of the oceans, the trajectory of a cannonball, and for more than 2 centuries, it was one of the foundational pillars of physics. But Newton's gravity had a flaw. It assumed that gravitational effects propagated instantaneously, that if the sun were suddenly to disappear, the Earth would immediately fly off in a straight line, without the 8 minutes of delay that light from the sun takes to reach us. This instantaneous action at a distance was philosophically troubling, and it became physically problematic when Einstein developed special relativity in 1905 and established that nothing, no signal, no influence, no information of any kind can travel faster than the speed of light. Einstein spent the decade following special relativity working out how to reconcile gravity with the speed limit of light, and the result was general relativity. In Einstein's picture, space and time are not separate things, but aspects of a single four-dimensional entity called spacetime. And mass and energy do not pull on other masses through a mysterious force across empty space. They curve the fabric of spacetime around them, and other objects, including photons of light, follow the straightest possible paths through this curved spacetime. What we experience as the gravitational force is the effect of curved spacetime on the paths of freely moving objects. One of the immediate predictions of general relativity was that sufficiently massive objects could curve spacetime so severely that the curvature became self-reinforcing, that beyond a certain density, the gravitational collapse could not be halted, and the result would be a region of spacetime from which nothing could escape. The radius at which this happens, the radius within which an object must be compressed for it to collapse into a black hole, is the Schwarzschild radius, named for the German physicist Karl Schwarzschild, who derived it within weeks of Einstein publishing the general theory of relativity. The Schwarzschild radius of an object is proportional to its mass and inversely proportional to the speed of light squared. For an object as massive as the Sun, the Schwarzschild radius is about 3 kilometers. This means that if you could somehow compress the entire mass of the Sun into a sphere 3 kilometers in radius, it would collapse into a black hole. For the Earth, the Schwarzschild radius is about 9 millimeters. You would need to compress the entire Earth into a sphere the size of a marble. The boundary of a black hole, the surface at the Schwarzschild radius, is called the event horizon. It is not a physical surface, but a mathematical boundary, a point of no return. Once anything, matter, radiation, information of any kind, crosses the event horizon, it is permanently trapped inside. The escape velocity from within the event horizon exceeds the speed of light, and since nothing can travel faster than light, nothing can escape. From the outside, a black hole appears completely black. No light escapes from it. No signal comes out. It absorbs everything that falls in and emits nothing in return. Or so classical general relativity predicts. But classical general relativity does not include quantum mechanics, and quantum mechanics changes everything. Drift a little deeper now. The room is quiet. The night is holding you, and the story moves into the quantum world, into the strange, probabilistic, fundamentally uncertain realm of physics at the smallest scales, and what happens when that realm encounters the extreme gravity of a black hole. Quantum mechanics tells us that the vacuum of empty space is not truly empty. At the quantum level, space is a seething foam of virtual particles, pairs of particles and antiparticles that pop into existence from the energy of the quantum vacuum, exist for a brief moment, and then annihilate each other, returning their borrowed energy. This is permitted by Heisenberg's uncertainty principle, which allows energy to be borrowed from the vacuum for short periods, provided it is returned quickly enough. Under ordinary circumstances, this quantum fluctuation of the vacuum has no observable consequences. The virtual particle pairs appear and annihilate so quickly that they leave no lasting trace. But near a black hole event horizon, something remarkable can happen. Stephen Hawking realized in 1974 that near the event horizon of a black hole, the intense gravitational field can interact with these virtual particle pairs in a way that prevents them from annihilating. If one of the pair falls inside the event horizon while the other escapes, the infalling particle carries negative energy into the black hole, reducing its mass slightly, while the escaping particle carries positive energy away from the black hole. From the perspective of a distant observer, the black hole appears to be emitting radiation, a steady thermal glow of particles escaping from the region near the event horizon. This is Hawking radiation. It is real radiation, not virtual, not borrowed, but genuinely produced at the expense of the black hole's mass. And it has a specific temperature, now called the Hawking temperature, that is inversely proportional to the mass of the black hole. The more massive the black hole, the colder it is. The less massive, the hotter. The mathematics of this derivation is formidably complex. It requires a full quantum field theory calculation in curved spacetime, the kind of calculation that requires graduate-level physics and advanced mathematics. But the result, the Hawking temperature, can be derived with remarkable accuracy using nothing more than dimensional analysis, the technique of combining the fundamental constants of nature in the unique way that produces a temperature. The fundamental constants relevant to Hawking radiation are 3 in number: the reduced Planck constant, which sets the scale of quantum effects; Newton's gravitational constant, which sets the strength of gravity; and the speed of light, which sets the scale of relativistic effects. These 3 constants, combined in the unique combination that has dimensions of temperature divided by mass, give the Hawking temperature, and that combination is precisely Planck's constant times the speed of light cubed, divided by Newton's gravitational constant times Boltzmann's constant times the mass of the black hole. The exact derivation includes a numerical factor of 1/8 pi, but the structure of the formula is completely determined by dimensional analysis alone. This is one of the most striking things about the Hawking temperature formula. It contains all 3 fundamental constants that define the regimes of physics: Planck's constant for quantum mechanics, Newton's constant for gravity, and the speed of light for relativity. Hawking radiation is genuinely a quantum gravitational phenomenon, a place where all 3 frameworks of modern physics come together simultaneously. And the temperature it predicts, for black holes of stellar mass, is extraordinarily small, about 20 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe, far too cold to detect with any current instrument. The discovery of Hawking radiation immediately raised a question about black hole thermodynamics. If a black hole has a temperature, does it also have an entropy? Entropy is the fundamental quantity of thermodynamics, the measure of the number of microscopic configurations of a system that correspond to the same macroscopic appearance. A system with high entropy can arrange its microscopic components in an enormous number of ways while maintaining the same overall appearance. A system with low entropy has few microscopic configurations available to it. The second law of thermodynamics states that the entropy of an isolated system never decreases. Processes in nature always move in the direction of increasing disorder, increasing entropy, increasing the number of available microscopic configurations. The connection between entropy and black holes was first proposed by Jacob Bekenstein in 1972, 2 years before Hawking's radiation calculation. Bekenstein noticed something remarkable about the area of the black hole event horizon. It has a property that is identical in behavior to entropy. Just as entropy can only increase with time, the second law of thermodynamics, the area of the event horizon can only increase with time as long as matter and energy are falling in. The area never decreases. This parallel was too precise to be a coincidence. Bekenstein proposed that the entropy of a black hole was proportional to the area of its event horizon. The more area, the more entropy. The entropy of a black hole measures how much information about everything that has ever fallen inside is hidden behind the event horizon. Hawking's calculation confirmed and quantified this proposal. The exact Bekenstein-Hawking entropy formula states that the entropy of a black hole is equal to Boltzmann's constant times the area of the event horizon, divided by 4 times the Planck length squared. The Planck length is the fundamental quantum gravitational length scale, approximately 10 to the negative 35 meters, the smallest meaningful distance that the laws of physics, as we currently understand them, can describe. And the entropy of a black hole is proportional to the area of its event horizon measured in units of the Planck area. This is an extraordinary result. The entropy and therefore the information content of a black hole is encoded in its surface area, not its volume. This is deeply counterintuitive. We normally think of the information content of a system as proportional to its volume. The number of things inside a box grows with the box's volume, not with its surface area. But for a black hole, the information content grows with the surface area of the event horizon. More matter inside a bigger black hole means a larger horizon, and the information encoded on that horizon grows with the area. This suggests something profound about the nature of space and information, something we will return to when we discuss the holographic principle. But first, let us follow the consequences of Hawking radiation to their logical conclusion. As you rest in the deepening quiet of this night, let the next part of the story settle gently. We have established that black holes emit Hawking radiation, a faint thermal glow at a temperature inversely proportional to the black hole's mass. And we have established that this radiation is emitted at the expense of the black hole's mass. The infalling negative energy partner particle reduces the black hole's mass slightly with each emission. Over time, the black hole loses mass to Hawking radiation. But how long does it take to evaporate completely? The calculation requires combining the Hawking temperature with the Stefan-Boltzmann law, the law that governs how much power per unit area an object radiates when it is at a given temperature. The Stefan-Boltzmann law, which itself can be derived by dimensional analysis from the speed of light, Planck's constant, and Boltzmann's constant, states that the power per unit area radiated is proportional to the fourth power of the temperature. For a black hole, this means the total power radiated is proportional to the fourth power of the Hawking temperature times the area of the event horizon. Since the Hawking temperature is inversely proportional to the mass, and the area of the event horizon is proportional to the square of the mass, the total power radiated is proportional to the inverse square of the mass. As the black hole loses mass, its temperature rises, it radiates more powerfully, loses mass faster, gets hotter still, a runaway process that accelerates until the very end. When you integrate this differential equation, when you solve for how long it takes the mass to go from its initial value to zero, the answer is that the evaporation time is proportional to the cube of the initial mass. A black hole of 3 solar masses, a small stellar black hole by astrophysical standards, would take approximately 10 to the 68 years to evaporate. The current age of the universe is about 13.8 billion years, or approximately 10 to the 10 years. The evaporation time of a stellar black hole is therefore some 58 orders of magnitude longer than the current age of the universe. These black holes are essentially eternal on any timescale relevant to human experience or even to the lifetime of stars and galaxies. But the evaporation time depends on the cube of the initial mass. This means that a sufficiently small black hole could have an evaporation time comparable to the age of the universe. A black hole formed with the mass of an asteroid, roughly 10 to the 11 kilograms, about 100 billion kilograms, would have an evaporation time of approximately 13.8 billion years. If such primordial black holes were created in the violent conditions of the early universe, they could be completing their evaporation right now. The final moments of their evaporation would produce a burst of high-energy gamma radiation, observable, in principle, with current or near-future gamma-ray telescopes. The energy released in the final second of a black hole's life is equivalent to the energy of approximately 100,000 hydrogen bombs, all released in a brief, intense gamma-ray burst. Nothing of this nature has yet been observed, and primordial black holes of this mass remain a purely theoretical possibility. But the search is ongoing, and a detection would be one of the most spectacular confirmations of quantum gravitational physics ever achieved. Let your eyelids grow heavier as the story moves to its deepest and most philosophically challenging territory, the information paradox and the holographic principle that may resolve it. When Hawking discovered that black holes radiate, he quickly recognized a serious problem. The radiation emitted by a black hole, Hawking radiation, is thermal radiation. It is random, structureless, characterized entirely by the temperature of the black hole, which is determined by the black hole's mass. The radiation carries no information about what fell into the black hole to create it. Whether you threw a library of books, a collection of laptops, a human being, or a cloud of hydrogen gas into the black hole, the Hawking radiation emitted would be identical, characterized only by the total mass. This means that as the black hole evaporates, all the information about what fell inside is apparently lost. The black hole shrinks, radiates, shrinks further, and eventually disappears entirely, leaving behind only featureless thermal radiation that cannot be used to reconstruct any information about what went in. The information about the books, the laptops, the human being gone, permanently, irretrievably. This is the black hole information paradox, and it is a serious problem because quantum mechanics insists that information cannot be destroyed. One of the most fundamental principles of quantum mechanics, encoded in the Schrödinger equation, is that the evolution of a quantum system is unitary. This means that the information content of a system is preserved as it evolves. If you know the exact quantum state of a system at one time, you can in principle reconstruct its exact quantum state at any earlier time. Information is never created or destroyed, but Hawking radiation, as Hawking originally calculated it, appears to destroy information. The quantum state of everything that fell into the black hole is replaced by featureless thermal radiation. Unitarity is violated. A fundamental principle of quantum mechanics is contradicted. Either Hawking's calculation is wrong, or general relativity's picture of what happens inside a black hole is wrong, or quantum mechanics is wrong. One of our best theories of nature must break down. And the resolution of this paradox, the identification of which theory needs to be modified, and how, is one of the central unsolved problems in theoretical physics. One of the most compelling proposed resolutions is the holographic principle. The holographic principle arose from examining the Bekenstein-Hawking entropy formula more carefully. We established that the entropy of a black hole is proportional to the area of its event horizon, measured in units of the Planck area. The Planck area is approximately 10 to the negative 70 meters squared, the square of the Planck length, the fundamental quantum gravitational scale. Now, the entropy of a system, according to Boltzmann, is connected to the number of microscopic configurations of the system. The logarithm of the number of configurations is proportional to the entropy divided by Boltzmann's constant. If the entropy of a black hole is proportional to the area of its event horizon in Planck units, then the number of configurations of a black hole is 2 to the power of the number of Planck areas on the event horizon. This can be interpreted as follows. Imagine that the event horizon is covered with tiny Planck area pixels. Each pixel can be in one of two states, 0 or 1, like a bit of information. The total number of configurations is 2 to the number of pixels, and the entropy is proportional to the number of pixels, which is proportional to the area of the horizon. The information content of the black hole is encoded in these Planck-scale pixels on its surface. The implications are extraordinary. All the information about everything that has ever fallen into the black hole, every book, every laptop, every human being, is encoded in bits of information on the two-dimensional event horizon. The three-dimensional interior of the black hole is, in a sense, a projection of the two-dimensional information on the surface. The interior is a hologram, a three-dimensional image encoded on a two-dimensional boundary. And if this is true for black holes, it may be true for any region of space. Any volume of space may have its information content encoded on its boundary surface. The physics inside the volume is equivalent to the physics on the boundary. The three-dimensional universe we experience may be a hologram, an image projected from a two-dimensional surface that encodes all the information of everything we see and experience in 3 dimensions. This is the holographic principle, articulated most clearly by the physicist Leonard Susskind, who described the universe as a hologram, an image of reality coded on a distant 2-dimensional surface. Everything inside a region of space, he argued, can be described by bits of information restricted to the boundary. The holographic principle is not merely a philosophical speculation. It has been given concrete mathematical form within string theory, in what is known as the AD-SCFT correspondence, a precise duality between a gravitational theory in a curved spacetime and a quantum field theory living on the boundary of that spacetime. The correspondence has been verified in many specific calculations, and it represents the most complete and concrete realization of the holographic principle available. Within the holographic framework, the information paradox may be resolved. If the information about everything that falls into a black hole is encoded on the event horizon, then Hawking radiation, which comes from the vicinity of the horizon, can in principle carry that information out as the black hole evaporates. The radiation is not truly random and featureless. It is quantum mechanically entangled with the information on the horizon in a way that, over the full evaporation lifetime, encodes all the information that fell in. Unitarity is preserved. Information is not lost. The mechanism by which this happens, the precise way in which the information encoded on the horizon gets transferred to the outgoing Hawking radiation, is still not fully understood. But the holographic principle provides a framework in which the paradox can in principle be resolved, and the work of the past 3 decades has made significant progress in understanding the details. There is a remarkable fact about dimensional analysis, the technique we have used throughout this story to derive the properties of black holes, that deserves a moment's attention. Dimensional analysis is the art of constructing equations from the fundamental constants of nature by requiring that the dimensions on both sides of an equation match. It does not tell you the exact numerical coefficient, the factor of 1/8 pi in the Hawking temperature formula, or the factor of 1/4 in the entropy formula, but it does tell you the structure of the equation, the way the fundamental constants combine, and the way the result scales with the relevant physical parameters. What is remarkable is how far this simple technique takes you. From the requirement that the area of the event horizon must be a quantity with dimensions of length squared, constructed from Newton's constant, the speed of light, and the mass, we derived the Schwarzschild radius up to a numerical factor. From the requirement that the entropy must have dimensions of energy divided by temperature, constructed from Newton's constant, Planck's constant, the speed of light, and Boltzmann's constant, we derived the Bekenstein-Hawking entropy formula up to a numerical factor. From combining the entropy with the first law of thermodynamics, we derived the Hawking temperature. From combining the temperature with the Stefan-Boltzmann law, we derived the evaporation time. At each step, the structure of the result was completely determined by dimensional analysis. The numerical factors required the full calculation, the quantum field theory in curved spacetime, the detailed derivation that Hawking carried out in 1974. But the structure, the relationships between the physical quantities, the scaling laws, all of this was accessible from high school mathematics and the careful tracking of dimensions. This is one of the deepest lessons of theoretical physics. The structure of physical laws is often determined by very general considerations, by symmetry, by dimensional consistency, by the requirement that the result depend only on the relevant parameters. The full calculation fills in the details, the precise numerical factors, the exact functional forms. But the structure was already there, waiting to be found by anyone willing to ask the right questions. Hawking asked the right questions. Bekenstein asked the right questions, and the answers they found have transformed our understanding of space, time, gravity, and information in ways that are still being fully worked out. The story of black holes and Hawking radiation is also a story about scientific courage, about the willingness to follow the mathematics wherever it leads, even when the destination is uncomfortable or counterintuitive. Stephen Hawking was 29 years old in 1973 when he began the calculation that would lead to Hawking radiation. He had already been diagnosed with ALS, amyotrophic lateral sclerosis, the progressive motor neuron disease that would eventually confine him to a wheelchair and leave him unable to speak without the assistance of a computer. But he was still at the height of his mathematical powers, able to carry out complex calculations in his head with a facility that astonished his colleagues. He approached the calculation expecting to prove something different. There had been proposals that black holes might produce some form of radiation through quantum effects near the horizon, and Hawking set out to demonstrate that this was not the case. Instead, he found that it was. The mathematics unambiguously predicted that black holes emit thermal radiation, that they have a temperature, that they lose mass and eventually evaporate. The result contradicted everything that classical general relativity predicted about black holes, and it violated his initial expectations. But the mathematics was clear, and Hawking reported it. The initial reaction from the physics community was skeptical. The calculation was so surprising, so far from what classical relativity predicted, that many physicists doubted it. But the calculation was correct, and over the years, the community came to accept it. Hawking radiation is now regarded as one of the most important theoretical predictions in modern physics, a result that, if confirmed experimentally, would represent a fundamental test of quantum gravitational effects. Experimental confirmation has not yet come. The Hawking temperature of any astrophysically realistic black hole is so far below the temperature of the cosmic microwave background that it is completely undetectable by any current or near-future instrument. The only hope of direct detection would be to observe the death throes of a primordial black hole, if such objects exist, or to create analog systems in the laboratory that mimic the physics of black hole horizons. Analog Hawking radiation has in fact been observed in several laboratory systems, in sonic black holes, where the event horizon is replaced by a surface across which sound cannot propagate, in optical systems, where the horizon is replaced by a boundary between regions of different effective speed of light, and in other carefully constructed quantum systems. These observations do not directly confirm the existence of Hawking radiation from astrophysical black holes, but they do confirm that the underlying physics of horizon-induced radiation is real. As the night deepens around you, let the grand arc of this story settle into a single, quiet image. A black hole in the deep darkness of interstellar space, long after all the stars have burned out, long after the galaxies have dispersed, and the universe has grown cold and dark. The black hole is slowly, imperceptibly glowing, radiating a faint quantum light so cold that it would be invisible to any detector, a temperature so low that no thermometer ever built could measure it. But it is there, a ghost of radiation, a quantum whisper from the edge of the event horizon. Over an incomprehensibly long time, a time measured in powers of 10 that dwarf the current age of the universe by dozens of orders of magnitude, the black hole is shrinking. Millimeter by millimeter, atom by atom, quantum fluctuation by quantum fluctuation, it is losing mass to the universe around it. The event horizon is receding. The Hawking temperature is rising, imperceptibly slowly, but rising. And all the information about everything that ever fell inside, every atom, every photon, every fragment of information about every object that was ever swallowed by this black hole over its billions of years of existence, is being encoded, in some way we do not yet fully understand, into the outgoing radiation. And then, finally, after a time so long that the word inconceivable does not begin to describe it, the black hole reaches the end of its life. In its final seconds, it radiates with the energy of 100,000 nuclear bombs, sending a brief, fierce burst of gamma radiation outward into the empty darkness. And then it is gone. The black hole has vanished. The event horizon has shrunk to nothing. The singularity has evaporated, and all the information, everything that fell in, encoded somehow in the quantum correlations of the outgoing radiation, is finally free, scattered across the universe in an infinite web of quantum entanglement. Whether this picture is exactly correct, whether information truly escapes, whether the holographic principle is exactly realized, whether the information paradox is truly resolved, remains unknown. But the framework is in place, the mathematics is deep and compelling, and the search for the final answer is one of the most active and most exciting in all of physics. There is one more beautiful thread in this story that connects everything we have discussed, a thread that runs from the smallest scales of physics to the largest, from the quantum vacuum to the structure of the universe. The Bekenstein-Hawking entropy formula tells us that the entropy of a black hole is proportional to the area of its event horizon in Planck units. The Planck area is approximately 10 to the negative 70 meters squared. A black hole the size of a proton, with a radius of about 10 to the negative 15 meters, would have an event horizon area of about 10 to the negative 30 meters squared. Dividing by the Planck area gives approximately 10 to the 41 Planck pixels. And the number of configurations of the black hole, 2 to the power of 10 to the 41, represents a quantity of information approximately equal to 10 to the 31 gigabytes. For comparison, the total digital data storage on all the computers in the world is approximately 10 to the 12 gigabytes. A proton-sized black hole could store more information than all the world's computers by a factor of 10 to the 19, 10 billion times more. And a larger black hole stores proportionally more. This is what it means for information to be stored on a surface rather than in a volume. The area of the event horizon grows as the square of the radius of the black hole, while the volume grows as the cube. For large black holes, the area is much smaller than the volume, and yet the information content is proportional to the smaller quantity, the area. The holographic encoding of information on surfaces is vastly more efficient than the volumetric encoding we are familiar with from everyday experience. And if the holographic principle is correct, if the information content of any region of space is proportional to the area of its boundary rather than its volume, then the universe as a whole, bounded by the cosmic horizon at the edge of the observable universe, has an information content proportional to the area of that horizon. The three-dimensional universe we inhabit, with all its complexity, all its history, all its matter and energy and quantum fields, is in some deep sense encoded on a two-dimensional surface. This is not merely a metaphor. It is a mathematical statement with precise consequences, consequences that can be tested, at least in certain idealized settings, through the AD-SCFT correspondence and related dualities. And it represents the deepest idea to emerge from the collision between general relativity and quantum mechanics. The idea that the dimensionality of space may not be as fundamental as we think, that the three dimensions we experience are in some sense a projection, and that the true arena of physical reality is the two-dimensional boundary on which information is encoded. To appreciate the full significance of Hawking radiation, it helps to understand the history of ideas about black holes, a history that is as much about human resistance to uncomfortable truths as it is about the mathematics that forced those truths upon us. When Carl Schwarzschild derived the exact solution to Einstein's field equations for a spherically symmetric mass in 1916, the solution contained a peculiar feature that most physicists, including Einstein himself, initially refused to take seriously. At the Schwarzschild radius, the critical distance at which the escape velocity equals the speed of light, the equations seem to break down. The metric, the mathematical object that describes the geometry of spacetime, appeared to become singular, to blow up to infinity. For decades, this apparent singularity was interpreted as a sign that the Schwarzschild solution broke down at that radius, that the mathematical descriptions ceased to be physically meaningful there, and that in reality, some other physics would prevent the density from ever reaching the critical value. Perhaps matter had some internal strength or pressure that would halt the collapse before the Schwarzschild radius was reached. Perhaps the idealized spherical symmetry of the solution was too special, and real collapsing matter would behave differently. The first serious mathematical analysis demonstrating that gravitational collapse to a black hole could actually occur in general relativity was the Oppenheimer-Snyder calculation of 1939, published in the same year as Oppenheimer's other famous paper on neutron stars. Oppenheimer and his student Hartland Snyder showed that a sufficiently massive ball of pressureless dust would collapse indefinitely, with an observer on the surface falling through the Schwarzschild radius in finite proper time, even though an external observer would see the collapse appearing to freeze at the Schwarzschild radius due to gravitational time dilation. This result was largely ignored. The world was about to enter the Second World War. Oppenheimer was about to become the scientific director of the Manhattan Project, and the physics community's attention was elsewhere. The existence of black holes as real physical objects remained controversial for decades. The decisive turning point came in the 1960s with the work of Roger Penrose and Stephen Hawking. Penrose proved in 1965 that the formation of a singularity, a point where the curvature of spacetime becomes infinite, is an inevitable consequence of gravitational collapse under very general conditions. Hawking extended Penrose's work to cosmological settings, proving that the Big Bang itself necessarily involved a singularity. These singularity theorems established that the extreme predictions of general relativity were not artifacts of special symmetry, but genuine generic features of the theory. With the reality of black holes established mathematically, and with their observational identification beginning in the late 1960s and 1970s through X-ray astronomy and the study of active galactic nuclei, the stage was set for the next great development, the application of quantum mechanics to black holes and the discovery of Hawking radiation. The concept of entropy in the context of black holes was not immediately obvious, and its proposal by Einstein in 1972 was initially controversial. Hawking himself was skeptical. The difficulty was that if a black hole has entropy, it must also have a temperature, and if it has a temperature, it must emit radiation. But classical general relativity predicts that nothing escapes from a black hole. A black hole with a temperature but no radiation would violate the laws of thermodynamics. The resolution came with Hawking's calculation in 1974, which showed that black holes do indeed emit radiation, quantum mechanical radiation, that had no classical analog. The skeptics were answered. Einstein's entropy was real, the temperature was real, the radiation was real, and the laws of thermodynamics applied to black holes in their full glory. The four laws of black hole thermodynamics, which parallel the four ordinary laws of thermodynamics, were established in this period. The zeroth law of black hole thermodynamics states that the surface gravity of a black hole is constant over the event horizon, analogous to the zeroth law of ordinary thermodynamics, which states that a system in thermal equilibrium has a uniform temperature. The first law relates changes in the black hole's mass to changes in its area and angular momentum, analogous to the first law of ordinary thermodynamics, relating changes in energy to heat and work. The second law states that the total area of all black hole event horizons in the universe never decreases, the black hole equivalent of the entropy always increasing. And the third law states that the surface gravity of a black hole cannot be reduced to zero by any finite sequence of operations, the black hole equivalent of the impossibility of reaching absolute zero. These four laws were not merely formal analogies. They were genuine physical laws, with quantum mechanics providing the final link that made the analogy exact and the temperature real. The surface gravity is not merely analogous to temperature, it is proportional to the temperature, with the Hawking calculation providing the exact proportionality constant. The area is not merely analogous to entropy, it is proportional to the entropy, with the Bekenstein-Hawking formula providing the exact proportionality constant. This unification of thermodynamics and general relativity, mediated by quantum mechanics, is one of the great theoretical achievements of 20th century physics. It suggests that thermodynamics, gravity, and quantum mechanics are not three separate theories, but three aspects of a single, deeper framework that we have not yet fully identified. The search for that framework is the search for quantum gravity. One of the most intriguing aspects of black hole physics is what it tells us about the nature of time. Inside a black hole, beyond the event horizon, the roles of space and time are interchanged in a specific mathematical sense. The radial coordinate, the distance from the center, becomes time-like inside the horizon, meaning that motion toward the central singularity is as inevitable as the forward passage of time outside the horizon. Just as you cannot avoid moving forward in time in ordinary experience, an observer inside the event horizon cannot avoid moving toward the singularity. The singularity is not a place in space, but a moment in time, a moment that lies inevitably in the future of every point inside the horizon. This interchange of space and time inside the event horizon is one of the most alien features of black hole physics and one of the most difficult to visualize intuitively. Outside the horizon, you can hover at a fixed distance from the black hole by firing rockets. You can resist the gravitational pull and remain stationary in space while time flows forward. Inside the horizon, you cannot resist the advance toward the singularity any more than you can resist the advance of time. The singularity is coming for you, and nothing, no rocket, no force, no physical process, can stop it. The Hawking radiation, being a quantum effect that occurs in the region near the event horizon rather than inside it, does not change this fundamental feature of black hole geometry. An infalling observer crossing the event horizon feels nothing special. The horizon is not a physical surface, and the crossing is locally unremarkable. It is only in retrospect, after the observer has crossed, that the event horizon is recognizable as the point of no return. This feature of the event horizon, its local invisibility to a falling observer, is one of the reasons why the information paradox is so subtle. An observer falling into a black hole does not experience any special event at the moment of crossing the horizon. The information they carry with them crosses the horizon smoothly, without any dramatic local event. And yet, according to the holographic principle, this information is somehow encoded on the horizon. A surface that, for the infalling observer, is not a surface at all, but an invisible mathematical boundary that has already been passed. The reconciliation of these two perspectives, the infalling observer who experiences nothing special at the horizon, and the external observer who sees the information encoded on the horizon, is one of the deep puzzles of black hole physics. The principle of black hole complementarity, proposed by Susskind and others, suggests that the two perspectives are not contradictory but complementary, that no single observer can ever access both descriptions simultaneously, and that the apparent contradiction disappears when you account for the limitations of what any given observer can actually observe. These ideas remain at the frontier of theoretical physics, debated and refined, but not yet definitively resolved. The black hole is not merely an extreme astrophysical object. It is a theoretical laboratory in which the deepest questions about the nature of space, time, information, and reality are played out in their most extreme and revealing form. The story of how black holes were observed, how objects predicted by pure mathematics were confirmed as real physical objects in the universe, is as dramatic in its own way as the theoretical story we have been telling. The first strong evidence for the existence of stellar mass black holes came from X-ray astronomy in the late 1960s and early 1970s. When a star in a binary system transfers mass to a compact companion, the infalling gas forms an accretion disk around the compact object and heats to temperatures of millions of degrees, emitting X-rays. The compact objects identified in several X-ray binary systems had masses too large to be neutron stars. They exceeded the Tolman-Oppenheimer-Volkoff limit, above which neutron degeneracy pressure cannot support the object against collapse. The only remaining explanation was that they were black holes. Cygnus X1, discovered in 1964 and identified as a black hole candidate in the early 1970s, became the first widely accepted stellar mass black hole. It has a mass of approximately 15 times the mass of the Sun, far exceeding the maximum mass of a neutron star. Hawking famously bet against its identification as a black hole in 1974, a hedge, he later admitted, against the possibility that his own theoretical work on black holes might be wrong. He conceded the bet in 1990. The evidence for supermassive black holes at the centers of galaxies accumulated over the same decades. The velocities of stars orbiting the center of the Milky Way galaxy were measured with increasing precision from the 1990s onward, and they indicated the presence of a compact mass of approximately 4 million solar masses at the galactic center. No known physical object other than a black hole could contain this much mass in such a small volume. The galactic center black hole, now named Sagittarius A star, was confirmed as a black hole through decades of patient observation. The ultimate confirmation of the existence of black holes, as predicted by general relativity, came with two landmark observations separated by just a few years. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time from the merger of two black holes approximately 13 billion light-years away. The gravitational wave signal matched the predictions of general relativity for a black hole merger with extraordinary precision, providing both the first direct detection of gravitational waves and the most direct confirmation of the existence of black holes as physical objects governed by general relativity. And in 2019, the Event Horizon Telescope, a global network of radio telescopes functioning as a single instrument with the resolving power of an Earth-sized telescope, produced the first direct image of a black hole shadow, the dark region at the center of the galaxy M87, surrounded by the bright ring of radiation from the accretion disk. The image matched the theoretical predictions of general relativity with remarkable fidelity. In 2022, the Event Horizon Telescope produced a second image, this time of Sagittarius A star, the black hole at the center of our own galaxy. These observational achievements confirmed what the mathematics had predicted for more than a century. Black holes are real. They exist in the universe in enormous numbers. Every galaxy appears to harbor a supermassive black hole at its center, and stellar mass black holes exist throughout galaxies in numbers estimated to be in the billions. They are not exotic theoretical curiosities, but fundamental constituents of the cosmic structure, and yet they remain, at the level of Hawking radiation and the information paradox, theoretical objects whose deepest properties await experimental confirmation. The quantum aspects of black holes, the Hawking radiation, the entropy, the information paradox, the holographic principle, have not yet been directly tested. They are predictions of a theoretical framework that we believe is correct, but that has not yet been confirmed at the quantum level. The search for that confirmation, whether through primordial black holes, laboratory analogs, or theoretical consistency with other well-tested predictions of quantum field theory and string theory, is one of the great ongoing adventures of modern physics. There is a philosophical dimension to the holographic principle that deserves attention as the story nears its close, a dimension that touches on some of the deepest questions about the nature of reality. The holographic principle suggests that the three-dimensional world we experience is not fundamental, that it is a kind of projection from a two-dimensional surface, that the true degrees of freedom of physical reality live not in the bulk of space, but on its boundary. This is a radical departure from common sense and from the framework of physics that we have developed over centuries. All of our direct experience is three-dimensional. We move through three dimensions. We perceive objects as having volume. We build our physical intuitions, our mathematics, our engineering on the assumption that space has three dimensions and that the information content of any region is proportional to its volume. The holographic principle says that this intuition, while practically useful, is not fundamentally correct. If the holographic principle is right, then three-dimensional space is emergent. It arises from something more fundamental in the same way that temperature and pressure arise from the motion of individual molecules. Temperature is not fundamental. It is an emergent property of the collective behavior of large numbers of molecules. Pressure is not fundamental. It is an emergent property of the average momentum transfer of molecules bouncing off surfaces. In the same way, three-dimensional space may not be fundamental. It may be an emergent property of a more fundamental, lower-dimensional quantum system. This idea is strange and counterintuitive, but it has a certain mathematical elegance. The AD-SCFT correspondence, the best-developed realization of the holographic principle, gives a precise mathematical dictionary between a gravitational theory in a certain curved spacetime and a quantum field theory living on the boundary of that spacetime. In this dictionary, the three spatial dimensions of the interior spacetime are encoded in the two spatial dimensions of the boundary theory. Gravity emerges from the quantum field theory on the boundary. Space itself, the three-dimensional arena in which gravitational physics takes place, is a derived quantity, not a fundamental one. This is perhaps the most radical implication of black hole physics for our understanding of reality. Starting from questions about what happens when matter falls into a black hole, questions of purely astrophysical origin, we have arrived at the suggestion that space itself is not fundamental, that it emerges from a more basic structure, and that the three-dimensional universe we inhabit is a holographic projection from a two-dimensional boundary. Whether this picture is correct in all its details remains to be seen, but the fact that consistent mathematical frameworks exist in which these ideas are realized precisely and quantitatively is remarkable. It suggests that we are on the right track, that the holographic principle, born from the study of the most extreme objects in the universe, is pointing toward a genuine feature of physical reality at the deepest level. As the final thread of this story comes to rest, consider the full arc of what we have explored tonight. We began with the geometry of the event horizon, the boundary of no return, and derived its area from dimensional analysis. We moved to entropy, the vast information content of a black hole encoded on its surface, and derived the Bekenstein-Hawking formula. We discovered Hawking radiation, the quantum glow of an evaporating black hole, and derived its temperature. We calculated the power output and the evaporation time, the slow, agonizing billion-year death of a black hole, and found that the final second releases the energy of 100,000 nuclear bombs. And we arrived at the information paradox, the deep conflict between general relativity's apparent destruction of information and quantum mechanics' insistence that information is preserved, and the holographic principle that may resolve it, by encoding all the information of the three-dimensional interior on the two-dimensional boundary. The story is not finished. The information paradox remains open. The holographic principle has not been fully proved. The quantum structure of spacetime at the Planck scale remains mysterious, and Hawking radiation itself, the central prediction that ties it all together, has not yet been directly observed from an astrophysical black hole. But the mathematics is compelling. The internal consistency, is remarkable. And the convergence of quantum mechanics, thermodynamics, and general relativity in the physics of black holes, all pointing toward a deeper framework in which information is fundamental, space is emergent, and the boundary is as real as the bulk, suggests that we are in the presence of something genuinely true about the deep structure of reality. Black holes are not just the darkest objects in the universe. They are windows into the deepest layers of physics. And the light they shed, however faint, however quantum, however theoretical, illuminates something profound about what the universe is and how it works. Rest in that thought tonight. The black holes are out there, in the dark between the stars, slowly glowing with their quantum light. Patient and ancient and extraordinary, holding within them the deepest questions in physics, and perhaps encoded on their horizons the beginnings of answers. The life of Stephen Hawking deserves more than a passing mention in any story about black holes and Hawking radiation, because his personal story is inseparable from the physics, and because it represents one of the most remarkable examples of intellectual courage in the history of science. Hawking was born in Oxford, England, in 1942, on the 300th anniversary of the death of Galileo, a coincidence he enjoyed noting. He was a bright but unremarkable student as a teenager, more interested in mathematics and physics than in the classical education his school emphasized. He entered Oxford University in 1959, where he read physics and found the coursework easy enough that he put in very little effort by his own later admission, spending much of his time rowing and socializing. He graduated with a first-class degree despite this and moved to Cambridge for graduate study in cosmology. It was during his first year at Cambridge, in 1963, that he was diagnosed with amyotrophic lateral sclerosis, ALS, a progressive neurodegenerative disease that attacks the motor neurons controlling voluntary movement. He was 21 years old. The doctors told him he had 2 to 3 years to live. His research director, Dennis Sciama, urged him to continue working despite the diagnosis, and the engagement with deep theoretical problems gave him a sense of purpose that helped him cope. Hawking not only survived but flourished. The disease progressed more slowly than predicted, and he lived for another 55 years, dying in 2018 at the age of 76. As his physical condition deteriorated through the 1960s and 1970s, his mathematical abilities adapted. Unable to write equations on paper or at a blackboard, he learned to perform complex calculations in his head, developing a geometric and visual approach to general relativity that allowed him to reason about spacetime in ways that avoided much of the algebraic complexity that other physicists had to work through explicitly. The Hawking radiation calculation of 1974 was one of the products of this adapted mathematical style. Unable to follow the usual approach of writing out the full quantum field theory calculation in detail, Hawking developed a geometric argument based on the behavior of quantum fields near the event horizon, tracking how the quantum vacuum was affected by the curvature of spacetime and deriving the thermal spectrum of the emitted radiation. The argument was elegant and physical, relying more on insight than on algebraic manipulation, and it produced one of the most important results in 20th century theoretical physics. Hawking lost the ability to speak in 1985, following a tracheotomy during a bout of pneumonia. He subsequently communicated through a computer speech synthesizer, controlled first by hand switches and later, as his hand function deteriorated, by a cheek muscle sensor triggered by slight movements of his face. His communication was slow, a few words per minute, but the depth and precision of his scientific and popular writing was undiminished. His book A Brief History of Time, published in 1988 and explaining the physics of black holes, the Big Bang, and the nature of time for a general audience, sold more than 10 million copies and remained on the Sunday Times bestseller list for more than 4 years, a record for a popular science book. Story of Hawking's life is a story about the separation of mind from body, about the persistence of one of the most powerful mathematical intellects in history in a body that progressively lost every voluntary function. It is also a story about the generosity of a person who, despite his condition, continued to engage with students, to communicate with the public, to appear in films and television programs, and to advocate for science, disability rights, and the future of humanity. He was not a saint. He had personal flaws and complicated relationships, like all human beings, but his intellectual contribution and his public role as a symbol of what human intelligence can achieve despite physical limitation were genuine and important. The physics he did, the Hawking radiation, the singularity theorems, the no-boundary proposal for the origin of the universe, the topological censorship theorem, and many other results, will outlast him by centuries. But the human story of how he did it, against what odds, with what adaptation and courage, is part of the story too. The quest to understand what lies beyond the event horizon, to answer the question of what happens to information that falls into a black hole, has driven some of the most creative and most technical theoretical physics of the past 50 years. And while the information paradox is not yet resolved, the attempts to resolve it have produced tools and ideas that have transformed our understanding of quantum gravity and string theory. One of the most important developments was the discovery of black hole complementarity by Leonard Susskind, Lars Thorlacius, and John Uglum in the early 1990s. Black hole complementarity is the proposal that the apparent contradiction between the infalling observer's experience and the external observer's description of information encoded on the horizon is not a real contradiction. It is a case of two mutually exclusive descriptions that cannot both be verified by any single observer. An observer outside the black hole sees information encoded on the hot membrane of the horizon, radiating back out in Hawking radiation as the black hole evaporates. An observer falling into the black hole passes through the horizon smoothly and sees no hot membrane, just empty space at the moment of crossing, with the information apparently lost inside. Both descriptions are correct for their respective observers. But no single observer can ever access both descriptions simultaneously. The external observer cannot fall in to check, and the infalling observer cannot send a signal back out to report their findings. This resolution may seem like a verbal trick, simply declaring the contradiction to be a matter of perspective rather than a genuine problem, but it has mathematical substance. The key insight is that quantum mechanics does not require that two descriptions be simultaneously accessible to be simultaneously true. The apparent contradiction only becomes a real contradiction if there is an observer who can verify both descriptions at once, and the causal structure of a black hole spacetime prevents this from ever happening. Black hole complementarity led naturally to the firewall paradox, proposed in 2012 by Ahmed Olmeri, Donald Marolf, Joseph Polchinski, and James Sully, often called the AMPS paper after their initials. The firewall paradox pointed out a tension within black hole complementarity itself. Quantum information theory requires that the Hawking radiation emitted in the early stages of the black hole's evaporation must be entangled with the radiation emitted later, in order to preserve the total quantum state of the radiation. But if the early radiation is entangled with the late radiation, it cannot also be entangled with the quantum fields inside the black hole. And this entanglement with the interior fields is precisely what is required for an infalling observer to pass through the horizon smoothly and find empty space. The resolution of the entanglement paradox apparently requires that the infalling observer, rather than passing through smooth empty space, encounters a wall of energetic quanta, a firewall at the horizon. The firewall paradox is one of the most actively discussed problems in theoretical physics today. It touches on the foundations of quantum mechanics, the nature of entanglement, the structure of spacetime near the horizon, and the limits of what complementarity can achieve. Various resolutions have been proposed, from modifications of quantum mechanics, to the conjecture that the interior of a black hole is connected to the early Hawking radiation through quantum wormholes, to the suggestion that the notion of a smooth horizon breaks down in a more subtle way than the original AMPS calculation suggested. The debate is ongoing and alive, which is exactly what healthy theoretical physics looks like. The questions are sharp, the tools are powerful, and the people working on the problem are among the most creative theoretical physicists of our time. The resolution, when it comes, will likely require new ideas about the relationship between entanglement, geometry, and information. Ideas that may ultimately be as transformative as the original discovery of Hawking radiation itself. There is a quiet beauty in the fact that the study of the most extreme objects in the universe leads, ultimately, to questions about the most fundamental nature of reality. Black holes are not just astrophysical curiosities. They are the places where the ordinary assumptions of physics break down, where the smooth spacetime of general relativity meets the quantum uncertainty of the very small, where the flow of information and the nature of entropy reveal something deep about what space and time fundamentally are. From the Schwarzschild radius to the Bekenstein-Hawking entropy, from the Hawking temperature to the information paradox, from the holographic principle to the firewall paradox, the study of black holes has generated some of the most profound and most challenging ideas in the history of physics. And it has done so not by finding easy answers, but by asking deeper and deeper questions, questions that reveal the inadequacy of our current frameworks and point toward the deeper theory that must lie beneath them. That deeper theory, quantum gravity, is still being sought, but the search has already taught us more than we expected. We have learned that entropy is not a property of volumes, but of surfaces. We have learned that information may be conserved even in the most extreme gravitational environments. We have learned that space itself may be emergent, that the three dimensions we inhabit may be a holographic projection from a more fundamental two-dimensional structure. And we have learned that the boundary of a region of space may be as physically real and as information-rich as the interior. These are not small lessons. They are among the most important things we have learned about the nature of reality in the past 50 years. And they all trace back, ultimately, to the simple question that motivated Hawking's 1974 calculation. What does quantum mechanics do to the event horizon of a black hole? The answer that it makes the horizon glow with a faint thermal radiation, that it gives the black hole a temperature and an entropy, that it ultimately causes the black hole to evaporate, opened a door that has not yet been fully explored. The rooms beyond that door contain the information paradox, the holographic principle, the firewall paradox, and perhaps, somewhere further in, the theory of quantum gravity that will unite everything we know about the universe into a single coherent framework. We are not yet there, but the door is open, the path is illuminated, and the most powerful minds of our generation are walking it. Rest now in the knowledge that the universe is deep, deeper than we yet understand, and revealing its depths slowly, patiently, one extraordinary discovery at a time. The black holes are out there, in the darkness between the galaxies, holding their secrets and glowing with their quantum light, waiting to be understood, patient and ancient and vast. And tonight, having followed the story from the Schwarzschild radius to the holographic principle, from the event horizon to the Hawking temperature, from the information paradox to the boundary of the knowable, you have walked a little further down that path than you have ever walked before. That is enough. That is more than enough. Let your breathing slow. Let your body settle. The universe will keep its secrets a little longer. And you can rest. Among the most haunting and beautiful aspects of black hole physics is what it tells us about the ultimate fate of the universe. In the very far future, a future so distant that the numbers required to describe it dwarf any scale of human experience, the universe will contain nothing but black holes. All the stars will have burned out. All the planets will have been scattered or consumed. All the ordinary matter will have been swallowed by black holes or dispersed into thin clouds of electrons and photons. The universe will be dark and cold, populated only by the slowly evaporating remnants of its most extreme objects. And then, one by one, the black holes will evaporate. The smallest ones first, the primordial black holes, if they exist, have perhaps already gone, flashing out in bursts of gamma radiation. The stellar mass black holes will take 10 to the 68 years. The supermassive black holes at the centers of galaxies, with masses of millions or billions of solar masses, will take correspondingly longer, up to 10 to the 100 years or more. But eventually, each one will reach the end of its evaporation. Each one will flash briefly and intensely in a burst of high-energy radiation, and each one will disappear. And after all the black holes are gone, after the last one has evaporated, the universe will contain nothing but a thin, cold gas of photons, electrons, and positrons, expanding forever into an infinite and empty darkness. The temperature of this final state will be essentially zero. The entropy will be maximal, no structure will remain, no complexity, no life, no information in any accessible form. This is the heat death of the universe, the final state of maximum entropy toward which the second law of thermodynamics inexorably drives all physical systems. And the evaporation of black holes through Hawking radiation is the last chapter of this story, the final process by which the universe completes its journey from the low entropy of the Big Bang to the maximum entropy of the heat death. But here is the extraordinary thing. If the holographic principle is correct, if information is conserved and encoded on the boundaries of regions of spacetime, then even in this final state, the information about everything that ever existed is not truly lost. It is encoded somewhere in the quantum correlations of the photons and particles that fill the universe. It cannot be read for all practical purposes. The information is so diluted and so entangled that reconstructing anything from it would require an intelligence of unimaginable power. But it is there, in principle, in the quantum state of the universe. This is the last promise of the holographic principle, not that information is accessible, it is not, but that it is preserved. That the universe, even in its most diluted and dispersed final state, carries within its quantum correlations the complete history of everything that has ever happened. Every star, every planet, every living being, every book, every thought, all of it encoded, infinitely diluted but never destroyed in the quantum state of a cold and empty universe. It is a cold comfort, but it is, in its way, a beautiful one. The search for quantum gravity, the theory that would unify general relativity and quantum mechanics into a single coherent framework, is the central unsolved problem of fundamental physics. And black holes, as we have seen throughout this story, are the place where the need for such a theory is most acute. General relativity predicts singularities, points where the curvature of spacetime becomes infinite and the theory breaks down. At the center of every black hole, the mathematics predicts a singularity. At the moment of the Big Bang, the mathematics predicts a singularity. These singularities are not physical predictions about what actually happens. They are signals that the theory has reached the limits of its validity, that something new must take over in the extreme conditions near the singularity. Quantum mechanics provides the tools to deal with the very small, but it does not, in its standard formulations, include gravity. Quantum field theory, the marriage of quantum mechanics and special relativity, is extraordinarily successful at describing the behavior of particles and fields in the absence of strong gravitational fields. But in the presence of the extreme gravitational fields near a black hole singularity, quantum field theory also breaks down. The energy densities become so high that quantum gravitational effects become important, and the theory cannot be applied without modification. String theory is one approach to quantum gravity. In string theory, the fundamental objects of nature are not point particles, but one-dimensional strings. vibrating at different frequencies to produce what appear at low energies as different particles. String theory automatically includes gravity. The graviton, the quantum particle of the gravitational field, appears naturally in the string spectrum, and it avoids the infinities that plague other approaches to quantum gravity by spreading the interactions over the finite size of the strings. String theory also provides the most concrete realization of the holographic principle through the AD-SCFT correspondence. Loop quantum gravity is another approach. In loop quantum gravity, spacetime itself is quantized, broken up into discrete units at the Planck scale, in the same way that energy is quantized in quantum mechanics. The smooth continuum of general relativity gives way, at the Planck scale, to a discrete network of quantum geometric states called spin networks. Loop quantum gravity predicts that the singularities of general relativity, the infinite density points at the centers of black holes and at the Big Bang, are resolved by quantum effects, replaced by states of finite but very high density from which the spacetime can expand or bounce. Neither string theory nor loop quantum gravity has yet produced a fully satisfactory and experimentally confirmed theory of quantum gravity. Both have achieved partial successes and both face significant open problems. The final theory may incorporate elements of both, or may be something entirely different, something not yet conceived, waiting for the right mind at the right moment to see it. What the study of black holes has established with mathematical certainty is that quantum gravity is needed. The information paradox cannot be resolved without it. The singularity theorems of general relativity point to its necessity. The Bekenstein-Hawking entropy formula, with its dependence on Newton's constant and Planck's constant simultaneously, is a quantum gravitational result. The resolution of the paradox requires a theory that treats gravity and quantum mechanics on equal footing. That theory is coming. It may not arrive in our lifetimes or in the lifetime of anyone alive today. But the questions are clear, the tools are powerful, and the people pursuing the answer are among the most brilliant of our generation. The light that Hawking shone on the event horizon of a black hole 50 years ago continues to illuminate the path forward, revealing in the quantum glow of a slowly evaporating object something fundamental about the nature of space, time, and reality. Let the story rest now. You have followed it from the basic geometry of a black hole, the curvature of spacetime so severe that nothing can escape, through the quantum physics of Hawking radiation and the thermodynamics of black hole entropy, through the information paradox and the holographic principle, through the life of Stephen Hawking and the observational confirmation of black holes, to the far future of the universe and the search for quantum gravity. It is a long journey and a deep one. And you have made it to the end. The universe contains black holes, billions of them, scattered through the galaxies, ranging in mass from a few times the mass of the Sun to billions of solar masses. They are real. They have been observed. They curve space-time, they devour matter, they generate gravitational waves when they collide, and they slowly evaporate through quantum processes over timescales that dwarf the age of the universe. And encoded on their event horizons, in Planck-scale pixels of information, is everything that has ever fallen inside them. Every atom, every photon, every fragment of complexity and structure and history that the universe has generated in 14 billion years of evolution. All of it encoded, in principle, on the boundary. All of it preserved, in principle, in the quantum state of the outgoing Hawking radiation. All of it waiting, in principle, to be decoded by some future intelligence with the tools and the knowledge to read it. We are not that intelligence, not yet, but we are asking the right questions. We are building the right tools. We are following the mathematics wherever it leads, even when it leads somewhere as strange and as counterintuitive as a three-dimensional universe that is really a hologram encoded on a two-dimensional surface. That is what physics does. That is what Hawking did. And tonight, you have followed along quietly at the pace of sleep through one of the deepest and most beautiful stories in the history of human knowledge. Rest now. The black holes will keep. The questions will keep, and the universe will keep unfolding its secrets, slowly and patiently, for anyone willing to listen. There is something worth dwelling on in the technique of dimensional analysis that we use throughout this story, not just as a mathematical tool, but as a way of thinking about physics. Dimensional analysis works because of a deep fact about physical reality. Every physical equation must be dimensionally consistent. The dimensions on the left side must match the dimensions on the right side. This is not a choice or a convention. It is a logical necessity. An equation that equates a length to a time is not just wrong, it is meaningless. The dimensions must match because the quantities on both sides of an equation must be measuring the same type of thing. This requirement of dimensional consistency, combined with knowledge of which physical constants are relevant to a problem, is often enough to determine the structure of the answer. The area of the event horizon must be built from Newton's constant, the speed of light, and the mass. These are the only dimensionful quantities available to a black hole described by classical general relativity. The only combination of these quantities with dimensions of area is g squared m squared divided by c to the fourth. Therefore, up to a numerical factor, the area of the event horizon must have this form. The full calculation confirms it. This is not guessing. It is reasoning from fundamental principles. The principle that only the right constants enter, that a classical gravitational problem should not involve Planck's constant, that a quantum problem should not involve Newton's gravitational constant, unless gravity is genuinely relevant, guides which constants to include. And the requirement of dimensional consistency then determines the structure of the result. The power of this approach becomes fully apparent when you see it applied to problems that require all three fundamental constants simultaneously. The Hawking temperature requires Newton's constant, Planck's constant, and the speed of light, all three simultaneously, in the unique combination that produces a quantity with dimensions of temperature divided by mass. This is not a coincidence. It is telling you that Hawking radiation is a genuinely quantum gravitational phenomenon, one that cannot be understood within general relativity alone or within quantum mechanics alone, but requires both simultaneously. Dimensional analysis is, in this sense, a way of listening to what the physics is telling you about itself. The dimensions of a quantity encode its fundamental nature. The combination of constants needed to construct that quantity reveals which areas of physics are relevant, and the requirement of dimensional consistency ensures that the structure of the result is correct, even when the numerical coefficient must await the full calculation. Max Planck himself used dimensional analysis to construct what are now called the Planck units: the Planck length, the Planck mass, the Planck time, and the Planck temperature. He noticed that from the three fundamental constants, Newton's gravitational constant, Planck's constant, and the speed of light, you could construct unique combinations with dimensions of length, mass, time, and temperature. These combinations define natural scales for physics in which all three fundamental frameworks, gravity, quantum mechanics, and relativity, are simultaneously important. The Planck length is approximately 10 to the negative 35 meters. The Planck time is approximately 5 times 10 to the negative 44 seconds. The Planck mass is approximately 22 micrograms, roughly the mass of a flea egg, as we noted in the Planck length episode. And the Planck temperature is approximately 1.4 times 10 to the 32 Kelvin, the temperature at which the thermal energy of a single particle equals its gravitational energy. These scales mark the frontier of our current physics. Below the Planck length, our theories break down. Before the Planck time, we cannot describe the state of the universe. Above the Planck temperature, we have no reliable theory. And at the Planck mass, concentrated into the Planck length, a black hole forms, the connection between quantum mechanics and gravity that is at the heart of this entire story. Everything in the story of black holes and Hawking radiation flows from these scales. The Hawking temperature of a solar mass black hole is so far below the Planck temperature that it is essentially zero on any natural scale. The area of its event horizon is so far above the Planck area that it contains an astronomical number of Planck pixels, and the evaporation time is so far above the Planck time that it dwarfs the age of the universe by unimaginable factors. Black holes span the full range of scales, from the Planck scale at the singularity to the astronomical scale of the event horizon, from the quantum scale of the Hawking temperature to the cosmic scale of the evaporation time. They are, in this sense, the most complete physical systems in nature, the only objects that require all of our physics simultaneously at every scale to be fully understood. And it is precisely this completeness that makes them such powerful windows into the deep structure of physical reality. They are not just extreme astrophysical objects. They are the natural laboratory for quantum gravity, the place where the need for a unified theory of all physics is most urgent and most clearly revealed. The study of black holes has taught us more about the nature of space, time, and information than any other single topic in the history of physics. And there is more to learn, much more. The door is open, the path is illuminated, the questions are clear. And somewhere in the mathematics that no one has yet written, the answer is waiting. As we come to the end of our journey tonight, the story can begin to settle around you. We have traveled from the basic geometry of event horizons, through the quantum physics of virtual particles and Hawking radiation, through the thermodynamics of black hole entropy and the information paradox, to the holographic principle and the idea that the universe itself may be a hologram. There is no need to hold any of that tightly now. You can let the details soften into impressions. The image of a black hole in infinite darkness, glowing with a quantum warmth so faint that no instrument has ever measured it. The image of information encoded in Planck-scale pixels on a two-dimensional horizon. The image of Hawking, young and brilliant, following the mathematics to a destination he had not expected, and reporting what he found with the honesty and courage that defines the best of science. Let these images drift through your awareness and dissolve, like starlight through dark water. The universe is very large and very old and very strange. It contains objects so extreme that the laws of physics strain to describe them. It contains mysteries so deep that our best theories break down at their edges. And it contains, hidden in the mathematics of those mysteries, hints of a deeper reality, a reality in which information is fundamental, in which space and time are emergent, in which the three dimensions we inhabit are a projection of something even more basic. We do not yet know what that something is, but the questions are clear, the mathematics is deep, and the search is ongoing. Let your breathing slow, let your body settle into wherever it is. The universe will keep unfolding on its own, just as it always has, steady, patient, and kind. Sleep well, good night, still drifting. Let the rain take over from here. Close your eyes and let it wash everything away.